I'll be talking on magnetic bearing. Very introductory lecture is there on this. I'll try to uh, cover basics so that people can follow this particular topic, and because my two fellow speakers are there, will be, I think, talking about more on the application part and or how this can be used for the industries. So this is the outline of my presentation, in which I'll just introduce the levitation, and then about the magnetic bearing. Different classifications of the bearings are available, and then on very basics of the active magnetic bearing. Especially when we are talking about active magnetic bearing, that means the property of the bearing can be changed during the operation, so actively, depending upon the requirement. And then advantage of the magnetic bearing as compared to the other kind of bearings which we have. A few industrial applications, especially the research wise, what people are doing it, I will give just glimpse of that. Also, I will give few slides on the what are the things we are doing at IIT Guwahati at research level on the magnetic bearing. So this levitation is, that long back people dreamed to levitate any object on the air, and in, I think, 1842, Earnshaw, he proved that a body cannot be levitated by a magnetic field if a body is in stationary condition, or the whatever the magnets are in the stationary conditions. So that 6 degree of freedom, as we know, of any particular body, so that cannot be controlled by this permanent magnets. But there are some exceptions to that. If we have some kind of active control of the magnetic field, then we can able to levitate the system. And there are some other exceptions are there. If we can have some constraint in the body, if we can restrict some degree of freedom of the body, then also with permanent magnet or combination of this active control, we can able to levitate. So I'll just brief how this particular magnetic bearing works. Lighter is there. Okay. So this is a rotor, as we know, which is generally conventionally supported by rolling element bearing or the fluid film bearing. So here, instead of that, we have electromagnet. This electromagnet is providing. Yeah. So this is providing some kind of magnetic field. So because this rotor is having weight, so this magnetic pull should counter that particular weight, so that this remains in this particular operating position. If any disturbance in this rotor is taking place because of whatever reason, this particular sensor, which is maintaining the gap between the rotor and the sensor, that senses there is some disturbance, and then it gives signal to the controller. Controller, based on the control law, it gives some signal to the amplifier what current in the electromagnet we should change to counter this particular disturbance by changing the magnetic pull or pull of this. So generally, this is a very simplified version of this. This kind of electromagnet can be there at the bottom also, and in the left and right side also. So 4 direction forces are pulling this particular rotor, and because of that, that is in the equilibrium position. So any disturbance in that will be controlled by the change in the electromagnet. I will just give a small video regarding the levitation. So this is a levitation by the permanent magnet of a spinning top. So now you can see that this particular rotating top is levitating on air, and this is due to the two magnets, one at the bottom which is ring type, another is there on the spinning top, that is also a ring type magnet, and you can see the magnetic field here. This particular top will be in equilibrium, where the magnetic field is getting changed direction. So this is one of the example how the levitation can help in the, but here once the stop is stopped rotating, it will drop. So the condition should be that it should keep rotating, then only we can able to levitate this. Sorry. So coming to the classification of bearing, based on various types it can be classified. One of them is the how the magnetic field is flowing through the shaft. So in this particular thing, this is the shaft. So these magnetic bearings are basically, you can see the field is in the parallel to the shaft's axis. And if you see the other view of the same magnetic bearing, in this particular case you can see the pole, north pole. So all are the north pole in this side of the magnetic bearing. This side is south pole, that is back of this. So because all poles are same, so that's why it is called homopolar. And this particular, as I mentioned earlier, to make the flow of the magnetic field closed, we need to have north and south pole. Okay, so here this is, we can able to count. Okay, this is 1, 2, 3. Similarly, if you count like this, there will be 8 such poles which is balancing the rotor. So this is, that's why it is called 8 pair pole magnetic bearing. This is one of the classification in which the magnetic flow is in the axial direction of the bearing. Another is this one, in which you can see now this is a magnetic actuator, this is the shaft. So this is one of the electromagnet. In this north to south the magnetic field is flowing, but now you can see the flow of the field is in the circumferential direction, not in the axial direction. And in this case also the magnetic force will pull in 3 directions to balance this particular rotor. So this is called 3 pair pole, and now you can see the in the axial direction as compared to the previous case. Now here north south, that kind of hetero, that's why it is called heteropolar bearings. This is another kind of classification based on the magnetic flow. This is also heteropolar, but now you can see there are 8 pair of poles. So this is 1, 2, 3, 4. So as compared to the previous in this particular case we need more complex control action. Here the control action, even number of poles are increased, we can have some kind of differential control action. So if we are increasing the force there, we can decrease the size by the same amount. Similarly other 2 pair. So this is, you can see there are 4 pair poles of the magnetic bearing. This is also hetero because you can see there is north south poles are there in this. So this is one of the actuator which we have in our lab. So this is the same 8 pole heteropolar magnetic actuator. So this is the same actuator. You can see there are 8 poles, pair poles in this. So this is a magnetic actuator. This is the shaft will carry this particular core, so that the magnetic losses are less, because steel losses will be more. So these are silicon steel. So in this particular case we need to provide core onto the shaft on the journal, so that the magnetic field will flow through this and the losses will be less as compared to the steel, pure steel. This is another type of bearing in which this is a thrust bearing. So this is also from our lab. So this is you can see that there are 4 pair of actuators are there. Top of this there will be a thrust disc, and above the disc there will be similar actuator will be there, and I think I'll just show this one. So you can see this is one of the pole I have shown in the previous slide. This is the disc, and at the bottom also there is a actuator. So magnetic field is flowing through this and like this. So both the actuators are pulling toward each other, and to counter the weight of this, obviously the upper actuator will be pulling more as compared to the lower one. And so this is the disc, and we should have this kind of actuator at the bottom and the top of the disc, which will be giving a thrust force to that. So you can see this is a vertical shaft, and the disc will have one at the bottom and at the top, and by that way it can be actuated in the vertical direction. So this is also from our lab, this particular rig which we are developing. Okay, and this is the magnetic field calculations we have done, in which you can see there are 2 poles and 2 this side. So there are 4 at the top and 4 at the bottom, and the magnetic pull we can able to calculate using this kind of softwares. Okay, so again classification, still I am continuing with that. So we can have either the passive magnetic bearing or the active magnetic bearing. So passive, as we already seen, the pure levitation. So in this we need to have some constraints, then only we can able to levitate the bearing, or otherwise it is unstable. But active magnetic bearing, we can able to control the things, but we require controller and the amplifier to do that. So this is one of another kind of classification we can able to do for the magnetic bearing. Sometimes we use combination of the electromagnet and the this permanent magnets. So with that we can have the either repulsive or attractive type of force to the shaft from the bearing. So based on the placement of the north and south pole, we can able to provide either repulsive force onto the shaft, or the attractive force onto the shaft. So this is another kind of classification. Sometimes, as I mentioned in the introductory slide, that we require displacement sensor to find out the operating position of the bearing, and if so, that is another kind of classification in which we use sensors, and sometimes we don't use sensors and displacement sensor, but Hall sensors based on the magnetic field. We can able to obtain the magnetic field intensity, and we can able to we can have the controlling action with that. Yeah. So as for the other kind of bearing, here also we can have axial or thrust magnetic bearing, radial or journal magnetic bearing. Even people have tried out the conical magnetic bearing, in which both combination of the radial and the axial thrust can be given, just like taper roller bearing. Similarly, here also people have tried conical magnetic bearing. There are several type of classification which we can able to do based on various criteria. These are some of the criteria. I will not go into much detail on this. So like according to the magnetic effect, electromagnetic bearing, and then there so many other classifications are there, like ferromagnetic effect, diametric effect, or superconducting material. So this is one of them. Then according to the magnetic effect, the continuation of that, electrodynamic bearing, in which permanent field or the AC current, induced current, controlled current with the permanent magnet combination. So many criteria are there in which people have tried the classification of this. So I think here we have lot of potential, especially because we are talking about standardization of the bearing. So classification could be one. I think standardization we should focus on this. Coming to the application, uh, gradually you will find that especially where the speed is the main criteria. If very high speed is there, when we are talking about 1 lakh RPM or more than that, then this magnetic bearing is having definitely advantage, and some of the uh, applications I'll be describing in the next slide. So this is one of the application in which you can see there is a shaft. There are 4 bearings, all are active magnetic bearing. The last one on this end, drive end, these are the bearing which is supporting the shaft on air with the magnetic actuation. In between there are 2 more magnetic bearing. They are providing some kind of aerodynamic instability or aerodynamic load which is actually there in the turbines. So we are in this particular case people are simulating aerodynamic effect through this magnetic bearing. So not only we can able to use the magnetic bearing for supporting, but any kind of excitation if you want to simulate, that also we can able to simulate using intermediate ones, and then we can able to check whether the supporting bearings can able to suppress that particular instability or not. So this is one of the application, and this is the test trick for that from some other author. So these 2 are the supporting bearing. These are the disturbance bearing which are simulating aerodynamic instability into the rotor, and they are controlling that particular instability. Another application, if there is some kind of rub between the rotor and stator, so this active magnetic bearing can help in that. We can have some operating position of the shaft, and if it is going beyond that, so this particular disc will touch stator. If this magnetic bearing is not there, this gap will close, and there will be rotor and stator interaction will take place. But if magnetic bearing is there, we can able to have operating position of that, and as soon as this particular disc is going close to the stator, this will actuate and that will suppress that particular disturbance. So this is another application of the magnetic bearing. So this is here you can see it is not supporting it, the shaft, but it is acting as a controller to suppress the vibration. This is the rig, I think the design in which this is the magnetic bearing. Yeah, this is a magnetic bearing, and here that particular stator rotor interaction was taking place, so they could able to suppress that. Another application is the oil valve which take place in hydrodynamic bearing. So these are the hydrodynamic bearing, the shaft is mounted on that, but this magnetic bearing is suppressing that particular phenomena if it is occurring based on if there is a large oscillations of the rotor, this magnetic actuator will act and that will suppress that particular disturbance. So this is another application of the magnetic bearing. This is the test trick the authors have designed. So you can see the rig, and this is the hydrodynamic bearing, and this is the magnetic bearing which is suppressing the oil valve phenomena. Another example is the compressors, the surge phenomena in which there is an instability condition of the pump. So that also, so here, so this is a compressor, you can see the blades of this, and this yellow, 2 yellow are the radial magnetic bearing. In between there is a thrust bearing. So here the impeller axial clearance was controlled by the thrust bearing, so that this compressor works in the optimal working condition or optimal efficiency conditions. So the axial thrust was controlled by this particular thrust bearing, and So to maintain the pump always in the best efficiency point. So that is not only the axial control, so radial control, but axial control also can help in increasing the performance of the bearing. Yeah. So some of the advantages as compared to the conventional bearing now I will highlight. So now you can see that because there is no lubricant, so all the problems of the lubrication, wear, tear will be eliminated here. And especially when we are talking about some application where this lubricant may contaminate the other working fluid. So this magnetic bearing is having advantage, like vacuum techniques in which, especially when we are talking about high speed, very high speed, here only friction is there between the air and the rotating rotor. So if we can provide the vacuum there, then that also those friction can also be eliminated in the bearing. So clean and sterile rooms like medicines and other applications, they have a lot of applications. Transport or aggressive or pure media where we don't want any lubricant to get into the actual the whatever the fluid we are handling or the material we are handling. So this is a typical actuator and the core of the magnetic bearing. So this is one of the turbomolecular pump which is used for separating the I think especially in the separators they use this, in which especially the like they are talking about the petroleum, if they want to separate various content of that, so they use this turbo molecular pump for that, and that operates at of the order of 1 lakh rpm or more than that. So for that conventional bearings will give very high much heat. Then the application is there in the centrifuge, and even in the now people are using for the flywheel energy storage system. Not only this is being used for the power plant, because very large flywheel can be made, and that can be floated on the air with the magnetic bearing, and energy can be stored. And whenever there is a deficiency of the electricity, this energy again can be taken out from this. Even for the e-mobility, some kind of I think energy flywheel they are using it in the automobile also. So I'll give some slides on that also, like this one. So already people are started developing.
Professor Tiwari,
Yes,
we have 5 more minutes.
yes, please. So this is the some kind of battery you can say, but this is not chemical battery. This is a flywheel is rotating inside and is levitated by magnetic bearing, and this is a mechanical energy storage, not the chemical one. So environment wise also is very good, and the life is also very high, of the order of 15 to 20 years life of this kind of storage system. So yeah, as I mentioned that the sealing and lubrication, those things will not be required then if we are using magnetic bearing. And this test rig was used for crack detection in the shaft. This is from our laboratory, and we developed some algorithm, and based on that we detect if there is a crack in the shaft, based on the measurement of the whatever the actuation force we are giving to the shaft during the rotation of the cracked shaft. So in the conventional bearing, the capacity of the bearing is, the load carrying capacity is fixed, but here we can able to change. Not only that, we can able to change the stiffness and damping property of that also, depending upon the requirement online. Okay. So this I already explained, that the magnetic bearing is not only to support the load, but to control if there is any disturbance, it can able to control that particular disturbance of the rotor, also we can able to give actuation force, like we have seen, we simulated the aerodynamic force, so that kind of force also we can able to simulate. So it acts as a bearing, actuator, and the some kind of exciter, we should say. Yeah, so I'll skip this part. I'll just go to the some case study which we are doing it. So this was I did in the Technical University of Darmstadt. So one test rig was there on the flexible, you can see very flexible shaft. So we did something on the dynamic balancing, flexible balancing of this rotor based on the magnetic bearing. So here you can see this aluminum frames are there, they are magnetic bearing, two magnetic bearing, and so we conducted some research to do the flexible rotor balancing of this. Then in here also in IIT Guwahati we developed rig in which we did the flexible rotor balancing for you can see there are two disc actuator here. This actuator is mounted there. This is the controller, and you can see that how much reduction in the vibration we could able to achieve after balancing. So this is a plot of that. This I already explained, the crack detection we did it with the magnetic bearing. So this is the overall circuit of the rig. This another rig we developed for the gear noise reduction and the finding the transmission error, how much quantifying the transmission error in the gear. So in this we used you can see there are two parallel shafts. This is the drive end and the gear is here, and two magnetic bearing we used to suppress the vibration, and we found that the noise was reduced, and also by the analytical approach we calculated the transmission error in the gears. So I think yeah, this is the another view of the same setup. So here all other power supplier, amplifier, displacement sensors, amplifier, these are there. Yeah, with this I will conclude. So this is my book on rotor systems, if you want to refer, and I have some lectures on the rotor dynamics, mechanical vibration in NPTEL. Some of you may be viewing that. If not, then you can use that. So if you have any questions.
Thank you, Professor Tiwari, for such an elegant talk. Now we'll take only two questions, none from the academicians, one from the manufacturer and one from the users. So if there is any question. Oh, if there is no question, then I have a question, and that is, what is the potential of using this magnetic bearing at elevated temperature? Say elevated temperature, I mean something around 800 and above.
So obviously materials, materials. So only limitation is the material if that can handle. Sir. So if material can be developed, then I think this can be. But 800 at present, I have not seen the application for that. But obviously, material is the limitation for that. Yeah. Yeah.
So that any variation that is there, all the significant, we have a complex system. Can we make it simple by using some other means so that we can
People are using now the hybrid bearings, in which permanent magnet and the electromagnets, both they are using it, and sometimes even they are using foil bearing and magnetic bearing, permanent magnets. So combination of that will be, I think, advantages in that. Yeah. So, yeah.
Mr. Pankaj Kumar from CKSP Dev Road. Whether this bearing can be used in turbocharger side of the turbine side of the turbocharger, because in turbine side the temperature will go up to 700 or 800 degrees centigrade. So whether this bearing is suitable for that or not? Because if binding is there, where this binding can be resistant to that surrounding temperature. Surrounding temperature may go 700 or 800 degrees centigrade, sir.
Not aware of that.
Yes.
Elevated temperature, magnetic property loses. So NASA has demonstrated, NASA has demonstrated up to 560 degrees centigrade for turbo machinery application. With the one paper is made. There is a maximum temperature so far. We have not seen.
So we will take rest of the questions at the end of the magnetic technical session. So we thank Professor Rajiv Tiwari for a beautiful lecture and addressing the questions of our audiences.